Hello, you absolute legends. My name is Eric J. Choi, and I'll be going over explainer video 8.2, which goes on about a problem describing a black hole, and the temperature of the black hole, and the entropy of the black hole as well. Damn, I said black hole a lot. Well, and jumping right into the problem. So, before we begin, I think I should warn you in advance that, in terms of references for this problem, there aren't any. To be more specific, because the professor hates the textbook, especially for this chapter because it doesn't explain much, the best bet you'll have towards finding references to find background information on these problems is the articles that he put up on the website, as well as his 2 lectures, because he goes in depth on some misunderstandings and the core concepts that you need to know to solve this explainer video and the past explainer video. So, now that we got that out of the way, we can start the problem. Black hole thermodynamics simplified. This problem is adapted from Cessna, and black holes are funny objects that are so dense that even light gets stuck inside them. So we have to do 2 things. We have to calculate the specific heat of a black hole and calculate the entropy of a black hole as well. Below, you'll see a diagram of the black hole, which is beautifully drawn by the professor, in which a singularity is right there. The mass is represented by m. There's the Schwarzschild radius, which is pretty good to know if you want to know like the background information of how this problem was inspired, but it's not very relevant in terms of solving the actual problem. And here's the rock or asteroid that's going to get thrown into the middle of the black hole, get absorbed in it, and the energy that it contributes will be understood later in the problem. And as I said before, this is background information that's useful to know, but not important for the problem. But this part right here is definitely important to the problem. The work by Stephen Hawking in finding the temperature in a black hole is equal to this: hc cubed over 8 pi gm Boltzmann constant, which with h is equal to 10 to the negative 34 joules seconds. That, along with Einstein's theory of relativity, E is equal to mc squared, will be very important in solving this problem. Now, even more formulas that will be important to solving this is Q is equal to MCAT, or Q is equal to MC times delta T, and also the understanding that if we took the rock and threw it into the black hole, we have to understand what changes in the energy of the black hole. So using Einstein's theory of relativity, it's already becoming useful already. E of the rock is equal to mc squared, and so when we calculate this part right here, the mass changes from m to m plus q, which is mc squared because we switched it out using this circled equation. We find that we can use this in our calculations for delta T and the heat capacity for the black hole. Now here comes the fun part: plugging and chugging. So T is equal to hc cubed over 8 pi k gm, which was mentioned in the Stephen Hawking equation. But if we, excuse the typo right there, if we differentiate this using dm, we end up getting dt over dm is equal to hc cubed over 8 pi k gm squared, with a negative, which is important later on. And we know that q is equal to mcat can be turned into dq is equal to mc dt. Using this as our foundation, we start plugging in these values one at a time in order to find this c value. So from this part right here, we're trying to replace this dt with this dt right here. So once we isolate out the dt, we find out it's equal to negative hc cubed over 8 pi k gm squared minus, no, that's not minus, that's dot, so multiply dm. And what's called E is equal to mc squared can be differentiated as well to become dE is equal to c squared dm, And we can plug that in for this part right here. So now that we know dq is equal to c squared dm, and we know that dt is equal to this, we plug and chug into the equation, which looks like this, and isolate out this c value, which I'm pretty sure you guys can solve on your own by pausing this, so I won't waste any more time on that. Until we finally find that the specific heat for a black hole is actually negative 8 pi kg over hc times m, which is really cool since the specific heat is actually negative in this case after all that work. Now that we go into the next part where we have to calculate the entropy, we know that 1 over T is equal to ds over dE under the condition that it's constant volume and constant number of particles. So using what we saw earlier, E is equal to mc squared and dE is equal to c squared dm, as I used in the previous part up there. Now we have to figure out how to make sure to find S. We know we have ds and we know the value of the other stuff such as T and dE. So by isolating ds out, we end up getting ds is equal to c squared over T of the black hole times m dm. Now all we have to do is take the integral of this, which is shown down here. And integral for solving this is actually pretty easy. All in all we have to do is multiply the front by 1/2 and square the value that we're differentiating, as shown over here, which ultimately ends up as 4 pi GkB Boltzmann's constant over hc times m squared. I'm pretty sure I included the work down here. So ds, which when we solve it out turns into 8 pi GkB all over hcm times dm. Once you multiply it by 1/2 and square the value that we're differentiating by, it ends up as this. I hope you guys understood it, you absolute legends.